Alright guys, so now we're going to be starting with biophysics. This is topic 2, X-ray and absorption, generation, and X-ray crystallography. And let's get right into it. Okay, so just before we get into it, I want to take a quick look at the electromagnetic spectrum. So we know the electromagnetic spectrum from the previous lesson. Here, the only thing I want to note is that we know that light can act like a wave, right? And that we know that as we go higher in frequency, then we go higher in energy and smaller in wavelength. Okay, so I want you guys to know that. And also, where do X-rays fall in this spectrum? On the higher energy side, okay? All right, and there's a couple of formulas you guys got to know. You guys probably know this already from chemistry, but it's E equals HF, where H is Planck's constant, which H equals 6.63 times 10 to the power negative 34. You don't need to memorize that. And F is a frequency. And E equals HC over lambda. Sorry, that's like not properly written. There you go, lambda. All right. We know the Bohr model, right? You draw the nucleus, and then you have energy levels, and electrons are here, right? But here it says kinetic energy. What was kinetic energy? We talked about this. It's half mv squared. Okay, that's the formula for it, equals ke. Now, what is this all trying to show us? This is to show us the difference in energy levels and what happens when an electron is ionized. What does ionization of an electron mean? That means if an electron exists here, if we give it enough energy, okay, from a photon or whatever, then it can actually get ionized from the atom. That means leave the atom, okay? And what happens when it leaves the atom? It has kinetic energy, and it stays with that, okay? Now, here, we need to know that if we want to ionize a inner shell electron, it takes more energy than, for example, an outer electron, right? Comparing these two lines. Now, how do we find the energy of this photon if, for example, it's leaving or coming down? It's E2 minus E1. Very simple. So imagine this E2 here is, for example, 4 joules, and E1 is 2 joules. Then you just need these two subtract by each other, which gives us the amount of energy. Okay, so this is just showing us that if we ionize an electron, what happens? It leaves the atom and it turns into kinetic energy. You don't need to know this, okay? You just need to know this. Again, this is not really X-ray. This is just kind of like the stuff you should know before that. Okay, now we're getting into X-rays. What is X-ray? It's a type of electromagnetic radiation. This is the electromagnetic spectrum, and the X-rays in it. Why is it special? It has a lot higher energy, which allows us to see and make pictures of things such as bones and stuff like that for medical usage and many other types of usages. Okay. As I said, the energy of an X-ray photon is much greater than visible light, and that's shown from here to here. Okay, now, an X-ray, there's the generation process, and there's the absorption process, okay? In the generation process, there's two types, characteristic and breaking. I'm going to explain all of them. I'm just kind of showing you how this lesson is going to go. And we have absorption. There's 3 types of absorption, photo effect, Compton effect, and pair production. Okay, so let's get right into it. This is just a slide showing you that what it can be used for. So, for example, computed tomography, we have conventional planar X-rays, stuff like that. All right, so how are X-rays generated? I said characteristic and breaking X-rays, and the mechanisms of absorption was the 3: pair production, Compton effect, photoelectric effect. Now let's get right into it. Okay, so characteristic X-rays. Okay, what do they depend on? The characteristic of what? The element being used, okay? The metal at the anode. Let me describe this for you guys. So we have a heated cathode, okay, that has a negative charge. Then we have the anode, okay? There's electrons here, okay, that are getting heated up, okay? They get shot towards this metal plate, this anode, okay? This anode, imagine it's stable, it has its electrons, okay, they're just chilling. Now, how do we create X-ray? We need a large amount of energy. What did we say does that? If we ionize an the innermost shell electron, that does it, right? So we have accelerated electron hits, this is the anode, and ionized. And what happens? It turns into kinetic energy, okay? Which equals what? Ke equals half mv squared. Okay? Then, once this happens, since this has so much potential and so much energy, this creates what? This creates an X-ray. Or sometimes a gamma ray. Okay? These are the steps, 3 steps. So, what happens? The electron gets accelerated and creates a vacancy in the inner electron. The vacancy is filled by an electron on a higher shell. The shell difference between the two shells is emitted as a photon. So, this is the diagram, okay? What happens? Accelerated electron hits the anode, okay? What happens? Hits the innermost electron. The electron gets ionized, okay? Now, there's no more electron in this K shell. What happens then? This electron, usually this one though, falls down, right? As we know, this is a great difference in energy level, and we're going to get into that in just a second, why it's greater. And this is of high energy, therefore creating an X-ray, or sometimes a hard or gamma ray. Okay? So that's how we do it. Let's just say the steps again. So we have a heated electrode, right? A heated cathode, negatively charged. Heats electrons, they get thrown out, okay? They hit the anode. Depending on the characteristic of the anode is the amount of energy you require to do this. If we have sufficient energy to ionize an innermost shell electron, this electron leaves the atom, and what happens? There's a vacancy. This vacancy is filled by a nearby shell, and this emits a photon due to its great energy. Okay, this is very important for you to understand. So, this is an energy level diagram. Again, sorry for my handwriting. Okay, this is the KLMN. What do these represent? If I draw a nucleus, this is the K shell, L shell, M, N. Okay, so they're energy levels. Now, here is the difference in energy. Okay, and this is very, very, very easy to understand. Okay, so let me draw this for you guys. Let's say we have a nucleus. Okay, then we have a bunch of energy levels. What's this called? The one in the innermost? K, L, M, keeps going. Okay. Now, if we have electrons here, okay, sorry, I can't do that. Let's say we have electrons here, doesn't really matter. Which one has the highest attraction to the nucleus? It would be this guy, okay? Why? Because it's the closest. We have a positive and a negative. Positive in the nucleus, negative as the electron. They're very, very tightly bounded to each other. So it requires a lot of energy to ionize the electron, okay? Therefore, there's a great deal of energy in between it, okay? There's a great deal of energy. Now, As we increase, this energy gets smaller and smaller, as we can see here. Give me 1 second. As we can see here, it's smaller and smaller and smaller until eventually it's barely even in the atom. Okay? What does this show? In a characteristic X-ray, we know that we need a lot of energy to create this photon, an X-ray photon. So we need a big energy change to create this photon. That's why we have to create a vacancy. Okay, imagine this is an electron, has to be ionized, right? Has to leave the atom for there to be a vacancy to emit this high energy. But, for example, if this happened in the outermost electron, or like one of the outer shells in this drop is not significant enough to make an X-ray because it's not of high energy. Okay. Okay, so what do we say? Characteristic depends on the characteristic of the element or atom, and it happens all in one step. So, boom, vacancy drops down, emits a photon. Now, we have breaking radiation. Remember, this is not spelt as breaking, okay? Not as in breaking a bond, but as a car braking. So, slowing down. Just in this one word, we could tell how it's generated. It is a type of radiation that keeps slowing down. What does that mean? So, we have the same exact setup. We have a heated cathode in a glass tube vacuum. The electrons are shot at the anode, and the anode is then ionized, okay? But here's the difference. They're not ionized all in one step. They're very random, actually, and they're typically between 20 and 150 kilo electron volts. What happens is, this energy comes in, hits the anode. These are all atoms of the anode. And what happens is, it hits one of the outer electrons, and it starts to slow down, and it keeps slowing down. And as this slows down, it loses and loses and loses energy, which this energy gets transformed into an X-ray photon. Imagine, you have a car, let's say a Bugatti. You're going 300 kilometers an hour, okay? And then you hit the brakes, right? As you hit the brakes, this braking radiation creates really, really high energy, which may turn your brake discs red, right? Or may create heat in the tires, for example. Okay, this is the same way. So here it says it in 4 steps. It says electrons are accelerated using a voltage, using an accelerating voltage at the cathode. Electrons gain large kinetic energy, right, and interact with the nuclei. So what does this mean? That means here, acceleration gets voltage. Here, it means that it hits the anode, right? Same thing as before. But here it says the accelerated energy here hits the anode and starts to slow down as it passes these nuclei. Okay, so accelerating braking charge generates electromagnetic radiation, where the nucleus attracts, thereby slows electrons passing nearby. So it goes like this. Whee! Right? And through this slowing down, it emits energy. Why? The first law of thermodynamics. Energy cannot be created or destroyed. So as this loses energy, something else has to gain energy. So boom. Okay? And the greater the deceleration, the higher the energy of the X-ray photon. That's how it works. Now, one thing I need to mention is, how do we know the formula? So this, of course, is kinetic energy. Fine. But when it slows down, is the kinetic energy minus the kinetic energy of the photon that's being emitted. And you can know that the frequency max, or the lowest lambda min, which is the wavelength, is equal to the highest energy. And if we can theoretically deaccelerate or slow this down or do this braking radiation all in only one step, okay, it would be the highest at this step, right? And that's how you calculate it. So HF max equals HC over lambda min, which you know this, or the kinetic energy formula. Very simple. So just to recap, I'm going to draw it out for you guys. We have a tube. Okay, we have an anode. We have a cathode. Okay, negative, positive, anode, cathode. Electrons are accelerated, hit the anode, and there's X-ray photons. Okay, this is characteristic X-ray, by the way. Well, actually, it's both characteristic and breaking. The setup. But here we're going to split it. Here's going to be characteristic and breaking X-ray generation. Okay. What happens in characteristic nuclei? We have a nucleus, energy levels. The photon comes. Sorry. The photon comes and hits the innermost shell electron. The innermost shell electron gets ionized. As this gets ionized, an electron from this drops down, creating high energy X-ray photon. Okay? Breaking, though, on the other hand, we're going to have multiple nuclei. For example, 1, 2, 1, 2, 1, 2. And imagine there's, what's it called? There is electrons on these energy levels. I'm not drawing it out, but that's how it is. Then we have the photon coming in, the X-ray photon. Sorry, not the X-ray photon. The accelerated electrons, and they get really, really close to the nucleus of the anode, and they scatter a little bit. So, ooh, 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 right? And it keeps going. And then we have loss of energy, which is released as an X-ray photon. Okay? All right. Then here it says, how does it look like on a graph? So what does the graph have? Wavelength, intensity. So do you think for a characteristic X-ray over here, as it's done in one step, is continuous or not? It's not. There you go. Great. And it looks like this. Okay? So something like at different energy levels. And it requires a high amount of energy. Okay? That's why it's on the lower end of the wavelengths. But for breaking, it's kind of on a random step, and it's what we use for medical diagnosis mostly, because you need lower energies. It's continuous. Happens a lot of random steps. It can go like this, emit photons here, there, creating the X-ray. Okay? Question is, can you have both? Yes, you can. Look, right here. You can have both. So, we're going to do the questions real quick. It says, why isn't the spectrum a sharp line? Because the kinetic energy of the electron is converted in several random steps. This is talking about breaking. We don't know exactly how many steps this is going to decelerate in, but we know that it will be a sharp line for characteristic because it happens in one step. Here it says, why does the limiting wavelength decrease with increasing voltage? Increasing voltage means what? Higher kinetic energy. Higher energy, which is inversely proportional to limiting wavelength. Then it says, can one generate characteristic and breaking radiation simultaneously? Yes. Here's the proof. It says, which X-ray is used in medical diagnostic procedures? As I said, the breaking radiation. Why? Because you can adjust the accelerating voltage to get the amount of energy you need without wasting energy. All right, here is just to show how absorption works. So we know that the attenuation coefficient, I'm going to explain what that means in a second, but of bones is higher, right, because it appears white, than soft tissue, because we can't see soft tissue. It goes right through, it just ionizes completely. What does that mean? this is what it is. So the attenuation coefficient is proportional to density and atomic number, okay? So it's how much does it, sorry, here's the exact definition. The attenuation coefficient is proportional to the density of the irradiated material and the third power of the effective atomic number. Okay, so what does this mean? This is how much is absorbed to 37%. Okay, now this is thickness, right? Because if something is thicker, then it's going to absorb more. And the attenuation coefficient shows how much absorption there is, right? So bones have high attenuation coefficient, represented by mu, okay? Then, for example, tissues. And that's pretty much what it's showing. So it's showing you why this is white and why this is black. All right, some formulas you need to know. Here, this is the exact definition. So it says, is the reciprocal of the distance where the intensity of the radiation decreases to e to the negative 1 times the initial value. What does this mean? 1 over x equals intensity e to the negative 1. Okay? Here, and here represent all the same thing. Now, this is showing you that bones have a higher attenuation coefficient than connective tissue, right? And if you take, this is a linear scale. If you take a logarithmic scale, it's a slope straight line. So how much does one thing absorb per unit thickness? How do you memorize this? If you guys did math in high school and you're familiar with it, this is an exponential function. What does it mean in this case? Intensity equals, so final intensity equals initial intensity times e to the power of negative mu x. Mu is attenuation coefficient and x is thickness. Okay? But pretty much the only thing you need to know here is if you have a higher attenuation coefficient, you have a steeper line than a less steep line. And then if you have for example, if bone was going to be here, then in less thickness, it'd be stronger than, for example, like this, which would be connective tissue. Okay, now we're getting to the absorption. We said there's 3. There's photo effect, Compton, and pair production. Okay, what is photo effect? Photo effect is when a photon is absorbed all of its energy to one electron in the inner shell. Okay, so what does that mean? Kind of like a characteristic X-ray, but don't get it confused. This X-ray photon hits this electron. This electron gets ionized. What do we say happens when it's ionized? Turns into kinetic energy. Okay, so this A represents ionization energy, or you could say work. So you're going to have work, so the ionization energy, plus the kinetic energy. This is the formula. So what is a photo effect? It's when a X-ray photon gives all of its energy to an inner electron, which leads to the ejection of the electron. Then we have Compton effect, which is kind of like braking radiation, but it's a little different. The X-ray photon comes, imparts some of its energy, and then scatters and does the same to other ones. So the Compton effect is where it transfers a part of its energy to an outer electron, and the electron is ejected, the photon is deflected, and its frequency decreases. So instead of it maybe being super strong, after it'll be something like this. And goes to the next atom. How do you calculate this? We know that the energy equals H times F. This is initial HF, so this guy, plus ionization energy plus kinetic energy. Why? Because this will emit ionization and kinetic energy, so these two, and this is the initial. Then we have pair production. This is very, very, very cool. So what do you have here? You have an X-ray photon. And what happens is you have a heavy nucleus. Why do you have a heavy nucleus? Imagine a gun. You shoot someone, not someone. You shoot, okay? And you have recoil. You need a heavy nucleus to keep this stable. You need a heavy hand to keep the gun stable so you don't hit yourself in the face with the recoil. So you have an X-ray photon. Due to this heavy nucleus, the X-ray photon is then converted to mass. This is Einstein's equation here. So E equals mc squared. And as it's converted to mass, it gets turned to an electron and a positron. Now, I don't really care about this electron. It kind of goes away. But this positron then gets annihilated, has annihilation. What is annihilation? Is a positron and an electron colliding, okay? And this makes a crazy amount of energy, which creates two, I think this is how you spell gamma photons in opposite directions. This is how you write it. Again, it's the same thing as E equals mc squared, but you're actually writing the mass of both positron and electron. All right, so now we're getting into X-ray crystallography. What is X-ray crystallography? So if I want to find out the structure of something, and I'm not sure how it's made, I use X-ray crystallography, because if I shoot an X-ray beam, then it will refract or reflect to show its structure. We're going to learn about that in just a second. So it's a technique based on diffraction, reflection, and refraction using X-rays from crystals, generating an interference pattern. Through this interference pattern, as you can see here, we can find out the structure of this material. Okay, this looks really complicated. It's not, don't worry. This, okay, is, I believe, Lau's interpretation. This is 5, we're not going to talk about this, and then this is Bragg's interpretation. So, what happens here, you have perpendicular X-ray beams to this guy, and they're parallel to one another. They hit the substance, the crystal, and they will be in coherence if their delta S is exactly multiples of wavelength. What does that mean? Okay, let me draw this for you guys. You have beams coming in. They go like this. Which one is longer, this one or this one? Of course, this one, right? By how much? By this guy. But let's say we have wavelengths. We have, okay, and we have, you see how they're still in coherence, right? I'm not the best at drawing this, but they're still in coherence. This means that this works, right? They will be in coherence at the correct places at the correct time. What does that mean? These waves will match each other and keep going, even though they have a difference of S. Okay? So that's called the path difference. And it has to be multiples of their wavelength. So it could be 2 or 3 or whatever. But it has to be the same. Because if these are not the same, then you're not going to get a bright spot of the scattering center. This is called scattering center. And you won't know the structure. So that's how that works. This is for a 5. But pretty much if you really do care for this, this is just showing you how to find the path difference when they're not getting shot exactly perpendicular to this line. I'm not really studying this, so I don't think you guys should, but pretty much this is the equation for it. It's not even highlighted, so I wouldn't care too much about it. This is just an add-on to this. I'm not really going over this. I know a lot of people don't even teach this, so pretty much it's just showing you different formulas on how to calculate the path difference of these guys when they're not perfectly perpendicular. Okay. So then we have interpretation according to Bragg. So when we went to Lau's principle, like interpretation, this was refraction. Okay, hit something, go somewhere else. In Bragg's interpretation, we have reflection. So hits something, gets reflected. Okay? And this is saying that X-rays can not only be scattered from the scattering centers of crystals, according to Lowell's version, but can also be reflected from the crystal planes. So it's saying that if you were to hit this, then something would happen. Okay? And that's it. So, and the path difference is calculated like this. Right, so as I mentioned, this is how we determine the structure of certain molecules. Again, this is a 5. I don't think it's very important. But let's say I had a molecule here, and I shot X-ray beams at it at perfectly perpendicular and parallel lines, and they went like this. And on this screen, they made bright and dark spots. Say the lines are dark spots. Then I could use a program to make an image of what it looked like. And that's the structure. Right? Something like this. Yeah, this is showing that we can use different programs to show different protein interactions, and we're going to learn about this in fluorescence as well. But this, again, X-ray crystallography is when we use an X-ray beam hitting a scattering center or a scattering plane in Bragg's interpretation to find out the structure of what we are monitoring. For example, a protein. And that is it. These are some questions you can ask yourself. So for example, how are the characteristic and breaking X-rays generated? What are the basic differences? So we know characteristics hits the anode, innermost shell electron leaves, there's a vacancy, drops down from the nearby energy level and creates this high difference in energy. Then what happens? X-ray is created. How it's breaking is random steps of the same thing, but instead of actually ionizing an energy, it goes through and decelerates through nucleuses and emits energy like that, which is an X-ray photon. What are the basic differences? One's continuous, one's discrete, one loses it all in one step, one has a bunch of random steps, stuff like that. Then it says, why is the spectrum of breaking X-ray continuous? Which formula describes the limiting frequency? Okay, so what do we say here? Breaking X-ray is continuous. Why? Because it loses its energy in many random steps, right? Because it goes like, wee. And here's like 1, 2, 3, for example, giving energy like this in X-ray photons. Then it says, what formula describes the limiting frequency, right? So that is limiting. Limiting frequency means what? Lowest energy. Okay, so if we come back here, let me show you guys. Here, right, so this is the max frequency, right? So HF max gives lambda minimum. Now we just switch this and this. So the minimum frequency would be the lowest frequency we have and the highest wavelength we have to find the lowest energy. That's all it is. You just switch that. And if they ask for the highest frequency, then you do the same thing. Let's go back to the questions. What are the mechanisms of X-ray absorption? So we said photo effect, photoelectric effect, Compton effect, and pair production. It says, what determines the attenuation coefficient of materials? How well I'm just going to say this. How well the material absorbs X-ray photons to the point where it decreases towards its 37%, so decrease of 63%, and this is equal to the reciprocal of the distance, so 1 over x. Then it says, which equation describes the decrease of X-ray intensity as a function of the thickness of the material? How can this be represented on a linear and logarithmic scale? So, which equation this is? Let me just read it again. Which equation describes the decrease as a function of the thickness? right? So this was I, final intensity equals I0 initial intensity times E negative mu x. Mu is a attenuation coefficient. X is what? Thickness of the material. Then it says, how can this be represented on a linear logarithmic scale? This is how you draw it. Make sure you indicate linear scale, log scale. You have to go like 0, 1, 2, intensity, and x thickness. Okay, let's say the same are written over here, but except it's log scale, so like log 1, log 2, etc. Okay, how does this look like? Woo. Sorry. You have I0, which is your initial intensity, and that's it. Then it says you can also do it as a linear logarithmic scale, so this it's just a straight line. There you go. That's that, and you go I0. Okay, you could also do other things, like for example, this would be I at E negative 1, which equals 1 over x, for example. Right, and you can do the same thing here. It says, what is the difference between laws and Bragg's interpretation of diffraction? Easy. So one says it's scattering centers with, I'll draw it for you guys. So Laws says X-ray photons come like this. You have scattering centers. Okay, and they get refracted, right? And here there is bright, dark spots on a screen. Then we make the structure. Okay, then Bragg's is very similar, but it says that we have a plane, you have scattering centers, whatever, but you can also use a scattering plane, which is this guy. Then X-ray photons come like this and get reflected on a screen, which again creates bright spots and dark spots. Then we get the structure. Okay. And last question for today, it says, what can we use X-ray crystallography for in practice? This is to determine molecular structures. For example, proteins. And this can be showed through these pictures, right? So if we didn't know these structures, we can use X-ray crystallography to find these out. And that is it for today's lesson. And I'll see you guys in the next one. Bye-bye.